תתנפה ידיים, אבל ככה מספיק רק כדי לקרוא דברים ולהבין.
כן? כאילו זה לא כמו הרצאה נגיד.
לא, זה לא כמו הרצאה, זה פחות רגור. אבל זה טוב, זה נותן לך ממש מצלח.
וואי, איפה מי?
Okay, so today, before we start linear response theory, I thought it could be valuable to show you another perspective on stuff we already did from the viewpoint of the Hubbard-Stratonovich transformation. So last time we saw, for example, I made some connections. We saw that the self-energy, the imaginary part of the self-energy of the fermions went like, what was it? Probably something like tilde lambda, I don't know, VF squared, omega squared, sine of omega or something. And my claim was that this is actually a version of the argument of Landau for the stability of a Fermi surface, because a phonon, sorry, this is a Yukawa model. This was for the Yukawa model. My argument was that this Yukawa boson, you can actually view it as an interaction. And if you have a finite mass, then this interaction is local. Okay, why is it local? For example, because if I Fourier transform, a 1 over something plus constant, like q squared plus constant, I get an exponentially decaying function. Okay, so I want to strengthen this intuition, okay, and to do that, let's see this connection between an interacting theory of fermions and the Yukawa model. Okay, and this is done through what is known as this Hubbard-Stratonovich transformation, and in high energy they call this bosonization. So in condensed matter we call something else bosonization, because in 1D you can there is a way to obtain the quasi-particles of an interacting 1D system given some constraints, of course, which is a Lattinger liquid, and that's what they call bosonization. But in high energy they call this bosonization, and the reason is, we'll see, because you start with the theory of fermions and you end up with a theory which is fully bosonic. Okay, so let's start from some action of this form. Okay, and specifically we will focus on the Coulomb interaction. In 3D this is Now, so two comments. One comment is that I'm kind of going to omit the spin summation from now on because it's going to be trivial. And what I'm going to tell you is generic, but I'm going to focus on the Coulomb interaction just because we can learn a few things along the way. Depending on how we proceed. Yeah. Okay. So we know that the partition function is just an integral over these fermionic fields of psi, e to the minus s of psi bar psi. Okay. And to perform this bosonization procedure, we note that you can always multiply, you always multiply this by the number 1 and you'll get the same result. But let me write 1 in a more complicated way. I can write 1 as some Gaussian integral where I absorb all the normalization factors of the Gaussian integral into the measure. The exponent of minus e squared over 2t L cubed sum over q phi cubed squared over v cubed. Also here I'm a bit sloppy with the notation. This q here is going to be a sum over both Matsubara frequencies and momentum, but this interaction here depends only on momentum. Okay? Good. Now we can make a transformation, a variable transformation. We can always transform the fields phi. You can transform phi such that it goes, say, phi q to phi q plus I t over e sum over k psi bar k plus q psi k. Okay, and what we have here, this is basically just the number operator. Okay, and I engineer this deliberately in a way, we'll see in a moment how it all works out nicely. Okay, and what that means that 1, so you could call this field like phi tilde or something, and now we're integrating over phi tilde because this is a constant shift, it doesn't change anything in the integral. So I'll just leave it the way it is. So I have d phi exponent of, now I need to be efficient with space, e squared divided by 2t L cubed sum over q, then I have something q something, okay, and the something is going to be phi q plus I t over e vq sum over k psi bar k plus q psi k, and here I have phi of minus q plus I t over e v minus q, but vq and v minus q are the same, so it doesn't really matter in this case. Sum over k prime, psi bar k prime minus q, psi k prime. And I'm using here k prime instead of k because these can multiply each other, so it's a bit ambiguous if you're doing the same k. Now, why did I do this shift? Why did I do this thing? Because now notice that if I open up these brackets, then the last term, when this multiplies this, I'm going to get exactly e to the minus this thing. Okay? So I get that this thing is an integral d phi exponent of minus e squared over tl cubed phi cubed squared. Then I have this multiplies that multiplies this, or the other way around.
Why don't you integrate over psi? This integral?
Why don't I integrate over psi? Where? Here there is no integral over psi. This is just the integral is over phi. I can't integrate over it. I just shifted. And why would I want to integrate over psi? I'm trying to reach, at this point, as far as you're concerned, and if you never saw this, then what I'm doing here is it's not clear what I'm doing. I'm still showing you something. But so the only thing you really need to worry about is whether each line you agree with each line. If you agree with it, then stay with it. Okay, you can ask questions in the end. Now there is the intermediate, never mind. The term where this multiplies that and this multiplies that. If you allow me to take q to minus q, and I can always do that. Oh, sorry, here there's a sum. Sum over q, phi q over v. If you allow me to take q to minus q and play with the k's and all that, then they are the same. So that just cancels the two. And now notice that this t falls with that t. The 2 falls because we have 2 terms. And one of these v's, so here you have v squared over v, you get just, this 1 over v cancels with that v. So, and here we have e squared and e. So overall we have minus ie over l cubed, sum over q and k, psi bar k plus q psi k phi of minus q. Okay, I had to choose either the phi of q or phi of minus q. I chose phi of minus q. And then the last term is just what we have there. So the last term becomes minus plus minus here, but then because of the 2 i's it's also another minus, so we get plus, we have so e cancels, blah 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 blah. So we have t over 2l cubed sum over k, k prime q, psi bar k plus q, psi k prime minus q, vq, psi k prime, psi k, and as I promised, I omitted the spin indices. So what this tells me, what did I learn from this? Well, I learned that exponent of minus t over 2l cubed sum over k, k prime, and q, psi bar k plus q, psi bar k prime minus q, V of Q psi K prime psi K, this whole thing is equal to the field integral d phi over the exponent of minus e squared over 2tl cubed sum over q phi q squared over vq minus ie over l cubed sum over q and k psi bar k plus q psi k phi minus q, which is what we wanted to obtain, because this means that if I plug this expression into this exponent, then the e to the minus this, okay, will just give me, I can substitute it with this field integral. Okay? So what I get is a no action. So I'm going to have minus what I have here.
Why?
Because if I want to interpret this as an action, or this, then it should come with a minus. Oh, yeah. So if I plug it into an action, what I have is a sum over k psi bar k g naught to the minus 1 psi k. Maybe here we can write k. K and Q are like 4 momenta. Then the second term is plus e squared over 2tl cubed sum over q phi q over v cubed. And the last term is the coupling term. Minus IE over L cubed, sum over K and Q, psi bar K plus Q, psi K, phi of minus Q. Now this is, to some extent, the Yukawa theory, right? Here we have the fermions, free fermions. Here we have free bosons. These bosons don't have any dynamics. They might be boring, but they are some boson field. And then we have the coupling. Now I want you to notice a few things, a few comments that we need to make. So the first thing is that VQ is the propagator of the auxiliary boson field phi. So the idea is that what we call this field an auxiliary field. Okay, because I made it up. It didn't exist. But this whole Hubbard-Stratonovich thing kind of makes you feel that everything is made up, right? We don't know what's real anymore. Because for all purposes, that might be the field that describes everything. We'll see in a moment. But the point is that this V of Q, as promised, is the propagator of phi. This gives us the intuition that I was trying to give you here, that we can interpret this diagram as, you know, here we have basically like we have a coupling, we have another coupling. This is like a IE, and then we have a propagator that connects them, VQ. Okay, and we'll see how it works out in a moment, but that's the first comment I wanted to make.
The boson is squared, right?
The boson is squared.
In the sum of
Oh, yes, yes. Otherwise, it would be a delta function.
Right.
Okay. The second thing is, in this case, V of Q is independent of omega, and therefore phi is a classical is naively classical. We'll see that it will develop dynamics. Phi is naively classical, but it will develop dynamics due to its coupling to psi, to the fermions. Another important comment, and this is, I think, by far the deepest and most important comment, is in this case the coupling to the fermions comes with a factor of I. This factor originates in the fact that the interaction is repulsive. Okay, so the point is, here we added this factor of I because this interaction is a repulsive interaction. When we have a repulsive interaction, then e to the minus s is e to the, something negative. Now you could ask, why did I do that? Like, why is that important? Because if I wouldn't put this I here, then I wouldn't get this plus here. It would be minus. And then the interaction I would get is attractive. Okay. So, and what limits me to do this is this first term here. I want to complete, there is basically a completion to a square. It starts here. Now, this I have to have it with a minus. Why? Because otherwise this Gaussian integral is not convergent. Okay? So that means that when I have a repulsive interaction, I have to couple with this I. Now, if you're a smarty pants, let's put it this way, you might say, wait a second. But I can choose the coupling at will. Like, I can make the coupling complex. There's nothing bad about a complex coupling. That's fine. Actually, whether it's an I or not an I is not the issue. The deep issue is whether the action that we get the action is complex or not. Because you could think about, you could open this coupling actually into two couplings, like one where you couple phi of q to rho of minus q, and one where you couple phi of minus q to rho of q, like here. And you remember that rho of q star is rho of minus q, and phi of q star is phi of minus q. So when we write these kind of terms, this is like, you know, a field coupling to some complex conjugate and the other way around. So if you write everything together, the point is that here they will have the same I, the same factor of I. It means that in this case, the action is not something plus its complex conjugate, but something actually minus its complex conjugate. There is an imaginary part to it. So we started from an integral over what naively is a real action, okay? Because we're doing, we're either thinking about this field integral as a Euclidean, as a field integral in Euclidean time, or as path integral way to compute a partition function. But following this Hubbard-Sirtonovich transformation, we got an action that is complex. Okay, and that's not an accident. Well, okay, this has a very deep meaning, and I'll try to explain it. So, I think, to some extent, my feeling is that this is one of the most okay, let me put it this way. I don't know if this is a trick that the devil pulled or not, but living at this era, what we know now, this looks like a very devilish trick, and I'll try to explain to you why. The point is this: if your action is real, if you do this transformation and your action is real, then it means that this field integral, despite the fact that this is a quantum theory, we just bosonized it. Oh, actually, I didn't bosonize it yet. I'll bosonize it in a moment. Sorry. What I wanted to say is that, where is our action?
Over there. Here.
It's here. Okay, this is the action. So in a moment, I'm going to integrate out these fermions. And when I'll do that, I'll obtain an action that is only bosonic. Okay, now fermions, if you want to simulate fermions, that's a headache, because fermions are Grassmann variables, and they have these weird commutation relations. But by going to bosons, we make our life easier because it's just numbers that we know how to deal with. Now, if the action that we get after this procedure is real, then we can treat each factor like a probability, like a Boltzmann or a Gibbs ensemble. Okay, so then you can. It turns out that there are efficient methods, like Monte Carlo simulations, where you use the metropolis algorithm, and you can actually simulate and obtain, at least for moderate size systems, you can obtain pretty good results. So you can actually predict what is going to be the behavior of this system. Okay, you can at least on a classical computer. Okay? Mm-hmm. But if the interaction is so what this tells us is that we have a good way of dealing with systems that have an attractive interaction. Okay? Now it somehow turns out that well, I don't know if that's true or not, but the systems that we're really interested in are electronic systems, and electronic systems are repulsive. So somehow, I don't know how this happens or how it comes to be, but it turns out that exactly the kind of systems that we're interested in, we cannot simulate. And the reason is because of this factor of I. So this, it's not a factor of I want you to think about it in terms of the fact that the action is complex. So once you have repulsive interactions, you're forced to have a complex action, and that means that the field integral cannot be interpreted as some probability. Because it cannot be interpreted as a probability, we cannot use a quantum Monte Carlo. By the way, if you want to understand this issue about Monte Carlo, the way you should really think about it is that once this action is complex, it means that this is like an oscillatory integral. And oscillatory integrals, they don't work well with random sampling. So maybe one needs to develop methods. It's an open question, like how to deal with these problems. But maybe one approach would be to try and generalize, methods for oscillatory integrals, regular integrals to functional integrals, to try and solve this problem. There might be other problems. Amir, for example, is actively pursuing. Also, Tzvi was involved in this at some point. Maybe he'll get back to it, in trying to perform integrals in the complex plane that can deal with this issue. So this is like a big open question, but I think it's a very deep issue, and this is known as the sign problem. So the fact that for a repulsive interaction, the action, the bosonic action that you get is complex, is known as the sign problem. Okay, and models that have the sign problem seem to be the most interesting ones. So all the quantum grand states, like spin liquids, topological order, all the juicy physics that's beyond statistical mechanics is in this sign problem. Because think about it for a moment. If you don't have a sign problem, then it's basically just like a stat mech problem. It's a classical problem. And if you were in the colloquium by Avi Klein, talked about superconductivity, and he was talking about these quantum critical points, and he was trying to give something that's talking about semi-classical physics. Probably went over your head to some extent, but this might be a connection or a way to understand it. What he's basically telling you is that for some reason, these quantum critical models seem to be classical in this sense, that they don't have this sign problem issue. Okay, they are like this semi-classical approximation, this semi-classical approach works. Okay, so now the last step is to integrate out the fermions. Now we integrate out the fermions. Meaning that we identify that this action is quadratic in the fermions, okay, and therefore we can integrate them out. So we can rewrite this action as minus e squared over 2l cubed t sum over q phi q squared over vq plus a sum over k and p psi bar k g to the minus 1 of k and p psi p, where g to the minus 1 of k and p is equal to g naught to the minus 1 of k delta of k and p minus I e over L cubed phi of k minus p. And
should it be a plus e squared over 2
first of all, yes, this.
Yes, yes,
Yeah. And this, I'm going to call this guy. Tough, Mark. Very stubborn. This guy, I'm going to call it G0 hat. And this guy, I'm going to call it phi hat. These are just matrices in K and P space, as you can see. This matrix is what we call a Toplitz matrix. This matrix is a trivial Toplitz matrix in the sense that it is diagonal. Okay, but a Toplitz matrix means that the value of the element depends only on the distance from the diagonal. Okay, but these are just matrices. Okay. Now, what this means, we know how to solve such integrals. I claim that z is equal to an integral over phi, right, times the determinant of this g, times e to the minus, and here we can let's denote it as S0 of phi, okay, where S0 of phi, because I don't want to write it many times, is just this e squared over 2l cubed t sum over q phi of q squared over v cubed, okay? Now this guy is equal to an integral d phi e to the minus s naught plus a ln of the determinant of g, of this g. Okay, how are we with time? Okay, now I want you to notice that det G is just a product over lambda, let's call it lambda J, which are the eigenvalues of G, okay? And therefore, ln of det G is just a sum over J ln of lambda J. So this ln here is a ln of a number. Right? This is a logarithm ln of a number. But then you can rewrite it as an integral d phi e to the minus s0 phi plus trace of ln g. And then this guy here is now a ln of a matrix, which is something different, and it's a generalized logarithm. We're thinking about it as a series of products of matrices. Okay, so it's a different object, and the reason it works is because you know, this sum of j ln lambda j, okay, is basically equivalent to trace, right, over a matrix. Okay, imagine that we have a matrix with ln lambda 1, ln lambda 2, ta 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 ta, right? But because this is a trace, I can plug in, you know, I can put u dagger here, where u and u dagger are the transformations that, you know, take these eigenvalues back to their original form g. And now, because you know, for each power I can reinsert these, this thing just quite trivially, this becomes equal to trace of ln of this g. Okay, and that's the origin of this thing, where ln of g is like a sum over, you know, n is equal to 1 to infinity. What is it? Minus 1 to the n over n, g to the n, something like that, right?
Right, so yeah.
What?
זה מינוס 1 ב-n ועוד n. כן.
Okay, so that's how we interpret it. And then for each order, you could imagine plugging in these u's and doing that math. So we've arrived at our action. This is the Hubbard-Sratonovich action. S Hubbard-Sratonovich is, which is a function of phi, only phi, is equal to e squared over 2l cubed t sum over q phi q squared over vq minus trace ln of this g to the minus 1. This is to the minus 1. Sorry, this is to the minus 1. Oh my god. This is to the minus 1. This is to the minus 1. Oh my god. Sorry. But you get the message. Everywhere it's to the minus 1. This is also to the minus 1. Okay. Sorry for all the minus 1s. It's, you know, we carry these minus 1s because then later it becomes convenient. Here it looks kind of stupid. Okay. And then this is our Hubbard-Sratonovich action. And this guy, so this matrix here, G, depends on phi through this term. But this action depends only on phi. And now we have a fully bosonic action. So everything I said before about, you know, the sign problem and stuff will show up here. Because if this coupling is complex, this action is going to be oscillatory. And if not, then not. That's one comment. What else did I want to say about this? Another important comment, which is made often, is that this action is exact. We didn't neglect anything. Okay? And that's what I was saying before about, you know, that this whole Hubbard-Sratonovich thing, it really how do you say like it really it makes you think what is real and what is not, because basically maybe fermions don't exist. See here, this action, it contains all the physics about fermions, right? Everything is there. We didn't neglect anything, but it's fully bosonic.
It's like this idea that all fermions are condensations of bosons.
That's so, yeah. So there is this philosophy. That's a different thing. So another thing, which is also a beautiful concept, is that one can I guess it's not surprising given this, but you can write a fully bosonic theory on the microscopic level, and in the low energy effective theory have emergent fermions. And then there are, as you know, Xiaogan Wen, for example, has this concept that possibly all fermions in the standard model are actually emergent particles. But who knows?
Yeah.
So,
I mean, I get the point that you can describe the system with an action that is fully bosonic, but you have the fermions. But isn't it like when you have a lattice of vibrational particles, and you describe them as phonons, which are like this vibrating modes?
So
you
you're
can
saying
still see the modes, but you don't see the particles. But
let me reinterpret what you're saying. You're saying, imagine that I have a crystal where the ions themselves in the crystal are fermionic particles like lithium. Still, when I do the phononic expansion, I get a bosonic mode. That's what you're asking? Is that along that line?
yes, just saying that it's
But
not that I don't have the fermions. It's just that.
But you see, that's why are phonons bosons is a very deep question. But to some extent, it's a very clever expansion, which circumvents a lot of complexities. But basically what happens is that when a lattice is fluctuating, ions never exchange their place. So any notion about their fermionic properties is unimportant. They're locally fluctuating in space. To that extent, they're kind of classical. So if you take a gas of particles and you start enhancing the interaction between them, initially they fluctuate everywhere, they're like free waves and stuff. If you enhance their interaction more and more and more, there's a certain point where their wave function will spontaneously break symmetry and they will localize in space. And then they essentially become classical. And that's what happened to a crystal. One of the reasons that helps them do that is that they're so heavy. So electrons are light and their quantum fluctuations are large, and that's why they stay quantum, if you like. Atoms not. Now another issue that's important to comment, which I think is very interesting, is that say you look at a model where you have electrons hopping on lattice sites with interaction. So sometimes we like to say that when they're free, there's no interaction, they're trivial. Okay? And then making the interaction large makes physics interesting. But actually it depends like how large, because if you make the interaction very large, then they again become classical and trivial. Like if you take the interaction to infinity. So it's actually only the intermediate regime which is interesting. And phonons are kind of beyond that. So the answer to your question, I'm kind of answering like LLM now. I'm making a large Z, and in the end I'm summarizing. So to summarize, the answer to your question is no, it's not the same. Phonons are a different story. Here, this is really exact. We neglected nothing. It's correct in all regimes. So for example, if I were to, melt your crystal and start allowing these, ions to kind of switch places, then it would really matter if these are lithium atoms or rubidium atoms or whatever. Okay, that's important. But here it's not. Okay, here we took everything exactly into account. So now let's take
I think you did neglect the spin, right?
we just
okay. So no. Okay.
It's not really neglect.
I didn't neglect anything. Okay. So you're asking a delicate question. You're saying, I think, okay, let me reinterpret your question. You're asking about the channel in which I chose to do the decomposition. I chose to do the decomposition in the density channel. You're asking where's the physics of the spin, right?
Yes.
So I could, for example, instead of doing the decomposition into phi, I could have done it in the exchange channel, where phi would be a vector, would be magnetization, basically. Then maybe like spin physics would be important. Yeah, that's a very important question, which I forgot. So thanks for asking that. We'll see in a moment. Okay, maybe in the exercise, which I'll write soon, I'll also let you exercise this idea. But the channel in which I choose to do the Hubbard-Sultanovich decomposition is really important for the kind of computation I want to make. Because this exercise, you know, it has some deep concepts in it. It can help me do quantum Monte Carlo and stuff like that. Also for quantum Monte Carlo, it's important how I do the decomposition actually. So, but as a concept, it might be a conceptual idea, but if I want it to help me do a calculation, it's important in which channel I choose to do the decomposition. Because that will affect the saddle point. If I take a saddle point, I take a saddle point with respect to phi. If I will do the decomposition with respect to the magnetic channel, the saddle point of that would look completely different from the saddle point with respect to phi. So both of the, it doesn't matter how I decompose it, all the physics is in there. It's in this trace local. Now if spin physics becomes important, it's just going to be very, very hard to see it from this. And you need to, what it will mean is that if I take a saddle point here, and then I start computing fluctuations around the saddle point, I'll find that the saddle point is very bad, and actually fluctuations around it are huge, and it goes to some, you know, it's controlled by paths that go crazy into the, you know, into the phase space, and only God knows how to deal with that. That's, you know, if spin physics becomes important, because that can happen. If the interaction is strong enough, you could have a situation where the system wants to become a ferromagnet, and then you can ask, how do I see a ferromagnet in this thing? Basically, it's somewhere hiding in there, very difficult to see. And actually, that's one of the things that at some point I was trying to solve this with Emil. We weren't thinking about magnetism, we were thinking about superconductivity. But, so I'll give you in the exercise, I'll let you do the same exercise with an attractive interaction and not decompose into density, but decompose into superconducting channel. And then you very nicely see that the saddle point of the Hubbard-Sultanovich action is exactly the BCI self-consistent equation. It's a very nice exercise. But one of the things we were trying to solve is exactly what you were asking now. Is, okay, let's say I'm stupid. Let's say I have an attractive interaction and I decompose it in the density channel instead of the superconducting channel. How do I see that this has a superconducting instability? And I think we almost know how to do that, but we have a few technical problems. Maybe actually that's a project you can pick on. Because if you've already asked the question and you're still searching for a project, that could be a perfect thing for you. I can show you the details. Actually, I don't know how I didn't think about that before. But so to proceed, okay, we need to do something. And that something is typically to assume that the saddle point is a good approximation, and that we can expand around the saddle point. And that's exactly what we were discussing before we went to the break, that in order for this approach to be useful to us, it has to be close to a saddle point. So we need to guess the decomposition correctly such that the saddle point is a good one. Now let's see what this gives us in this case. So we're going to assume a saddle point phi is equal to phi, saddle point is equal to 0, and expand around 0. Now I want to make a comment about this assumption, because we can just take straightforwardly, we can take the saddle point. We can write delta S to delta phi q, right? This just gives us E squared over 2L cubed T phi minus Q divided by VQ. And then we need to take the derivative of this guy. So So how do I take the derivative of this guy? So this is, sorry, not minus trace of, so the derivative with respect to phi of q means that we take first the derivative of this. So we have trace of g, okay, times the internal derivative gives us, so minus minus gives us a plus. So maybe I'll write it like this. So I get plus e over L cubed sum over, trace. And then I have this g. But then I need something to fix this matrix to be q. So I need phi to be fixed to q. So I'm going to write here delta. Okay, and delta is exactly the one that fixes that k minus p is q. So this thing is nothing but a sum over e squared over 2l cubed t phi minus q over vq plus e over l cubed sum over, say, k, and then we have this g, g of k and k plus q. Okay, because I want, you see, this is like a matrix in k and p, and I want the difference between them to be q. So that's exactly what I wrote. Okay. Now this equation, I demand that it's equal to 0. This is the saddle point approximation. And what you're looking at here, if you remember that V of Q is the Coulomb interaction, this is nothing but the self-consistent Poisson equation. But notice it's not the Poisson equation you're used to solving. Because the Poisson equation you're used to solving, this is indeed density. Right? But this is not G naught. This is not the density of, just whatever free distribution I chose. It includes also this phi. So it's a self-consistent equation. Okay? This is more sophisticated because I'm assuming that the charges create a potential, and then the potential affects the charges, and then the charges again.
It's like the screening of the...
It has everything in it. This is this is exactly the saddle point of this thing. But I'm going to assume that the configuration I'm looking for is a configuration where when everything settles down, saddle point, zero potential, zero field. So you could think about it like there's a background of the ions that is exactly balanced with the electrons, blah, blah, blah. Okay? So that's just an explanation. And one of the reasons I dwelled on this point for a moment is because now you see how to interpret this trace, how to take derivatives and stuff like that. So that's an important comment because you'll have that in the exercise. Now, trace. So now I want to expand around this saddle point. So to expand around the saddle point, I write formally this thing is equal to trace ln of g naught to the minus 1 minus phi. Okay, I'm just plugging in that definition up there. And this thing is trace ln of g naught to the minus 1 minus plus trace ln of identity minus g naught phi. Okay, and now we can expand this second term. So this term, we can call it S0 or something like that. This thing, if you think about it for a moment, well, let's call it S. Let's call it SF. Okay, because we already had this 0 for the field phi. If you think about this thing for a moment, yes?
Do we still have I there for the trace? EI?
I, yes.
Yeah.
Thanks. I. Of course. So if you think about this thing for a moment, this is exactly the free energy for the fermions. Okay? And way back when we learned how to perform this path integral. You know, when we did Matsubara sums and all that, that's how I can interpret this part. So this part is just the action of the fermions without the field. And this guy gives us all the corrections due to the interaction between them. So we can expand this. This thing becomes SF plus, then we have trace of G naught phi plus 1/2 trace of G naught phi G naught phi plus and now I can compute each one of them. So this guy is going to give you the energy of, you know, a constant density in the presence of a potential phi. I'm going to skip that. Okay, it appears in my notes. It's kind of straightforward. Let's jump to this guy. Okay? So I'm going to call this S2 Hubbard-Stratonovich. It's the Hubbard-Stratonovich action expanded to second order in phi. Actually not. No, I'm not going to denote it like that. I'm going to write S2 of Hubbard-Stratonovich is actually E squared over 2L cubed T sum over Q phi Q squared over VQ plus 1/2 trace of G naught phi G naught phi. Okay, that's what I wanted to write. So now let's compute this thing.
Would it be a minus?
Probably.
I mean, originally we have like minus trace of
Minus. Thanks. So 1/2 trace.
רגע, אולי לא, כי טור טיילור זה מינוס פעמיים, כן.
The Taylor series. So this should be with a minus. That's what you're saying.
Yes, and overall it's a plus.
Okay. Because this is a little bit smaller than 1.
Yes. Oh, okay.
Then trace this guy. This guy. Okay, this guy has, okay, so now I'm plugging in the expression. So, see this phi has, this factor gives me minus E squared over L to the 6th. Right? Then I have sum over, let me write here, K and Q. So, okay, these are like matrices. Okay, let me just write it first. So if I just multiply these matrices, this is like, you know, Gij Ah, by the way, this is G naught. G naught, G naught. Important G naught, yeah. So this is like G naught ij phi. This is like G naught ij phi jl G naught lk phi km, something like that. Okay, but this m and this I are the same because we're doing a trace, so I can just write here I. Now each one of these guys is a delta function. So here L is equal to K. That's this delta function that you see. Where is it? Here. This delta function. So here L and J is equal to L. I is equal to J. I is equal to J. Okay? So if I take that into account, I can basically call this I, then this is I. Then L is equal to K, so this is just, let's call it L. And then I is equal, so K is, so this becomes also L. Okay? So overall, I have just two momenta, I and L. And what you see here is that I have phi IL and phi LI. Okay? So overall, what I'm going to have here, to make a long story short, and then I have G at I and G at L. Okay, so if I interpret I minus L as being Q, okay, then that means that, and I will denote by K, then L is K plus Q, right? Okay, so all this is to say that what I have here is G naught of K, G naught of K plus Q times phi of Q squared. Okay, and now I can erase all this. And then this thing is equal to minus E squared over L cubed T, right? Pi of Q, phi of Q squared. And this pi is exactly the pi that we calculated last lecture. Right?
Right.
Do you remember him? Let's see if we can remember him by heart. Pi of Q is where is this minus? Pi of Q, we said, is the density of states, right? 1 minus omega over VF Q ln of omega minus VFQ, or maybe there's an I here. And here we assume, this is assuming that Q is much, much smaller than K. Right? Okay? And then we have two limits when VFQ is much, much greater than omega. We have n of 0 minus I omega over VFQ. Probably this comes without I don't know, maybe you guys look. And this is this Landau damping thing. And when VFQ is much smaller than omega, this guy goes like VFQ squared n of 0. This goes like n of 0 q squared divided by omega squared. Okay. So now we can summarize what we got for S2. So we get that S2 of Hubbard-Srutanovich is, sorry about that. Once once this happened to me in class, and I made up a joke that every time I get into a hot spot, I don't know the thing, then my ass starts playing classical music. Okay, I thought it was so good I have to repeat it. So here you have e squared over 2l cubed t sum over q, and then we have 1 over v of q plus, probably plus, right? Plus, because this comes with a minus. Where's the 1/2 factor? Where's the 1/2? Oh, this probably comes with a 1/2. Okay, good. And then I have here pi of q. Okay, and then phi of q squared. Okay, so this is the second order. Now, when we look at this expression, we can see that the correlator of phi, right, naively up to second order, only up to second order, the correlator in phi is 1 over VQ plus pi of Q, which is like VQ divided by 1 plus VQ pi of Q. Right? And this is exactly, if you remember that each bubble, each fermion loop gives us a minus sign, this is exactly, this. Right? So this is nothing but the RPA interaction. So we can interpret up to some factor here, okay? Up to some factor which depends on your definitions and so on. The correlator of this field phi, which couples to density, it's a conjugate that couples to fermion density, okay, gives you the RPA interaction. So this is another point where we get a very deep insight into what RPA really means, okay? Because what you understand is that you can interpret the correlator of the Hubbard-Srutanovich field as an effective interaction between the fermions, for example, or the Coulomb potential, if you like. But you also see that if you assume that it is Gaussian, basically what we're doing, it's like, when you do phonons and you expand, you expand the local potential up to harmonic order, and then everything is harmonic and nice and everything. So the same thing where the Coulomb field gives you RPA. So that's what RPA really amounts to. It's assuming that the fluctuations in phi are weak, okay, around the saddle point solution. Okay, so if the fluctuations are weak, RPA can work. So our RPA is like a semi-classical approximation around the saddle point. Okay, and when does that work? Well, that works in the large n limit. So if I multiply the number of fermions by a factor n, that will somehow pop up into this Green's function, and then when you expand in higher orders of phi, you'll find that these contributions are small. It happens when the coupling is weak. Okay, so let me write this exactly.
How is this equivalent to what we did in the homework? Because in question 3 we had to do this RPA where you have this.
But there you did it perturbative.
Yes, exactly.
Yeah.
But it's like.
Yeah. This. By the way, you have to understand here. There's something very deep here, because here we only expanded the trace log to second order. We didn't do a whole series. But this expansion to second order is equivalent to summing up perturbatively all diagrams. Summing up the entire geometric series.
Simple diagram.
Of
Right,
simply
random
connected,
place.
yeah.
Element is split. Like you sum their geometric series of a very simple diagram.
Yes.
Could have many other.
Totally. The simplest possible one, yes.
But in the homework we had something like we took the first order and then we assumed that every other order would be just like a geometric series, and then we summed over it and we got the same result.
Yes, you got the same result. You could get the exact same result you had in the homework. This is the charge channel. You could repeat the same thing by decomposing into spin, and you exactly get the same result.
Yes.
So what you would find for the spin channel is that this would be minus, and that would tell you that an instability is lurking, because you could actually make the mass disappear. And when the mass disappears, you could imagine that you have phi q squared, but then you also have a phi q to the fourth. This is writing it in a very sloppy manner because it's actually local in real space. So it's not phi q to the fourth, it's phi to the fourth, never mind. But then if whatever you have here vanishes, it's like transitioning from a potential that looks like this to a potential that looks like this. And then you have an instability. So that's your Stoner instability in the language of Hubbard-Stratonovich. And now because you're asked, I'm going to add it to the exercise next. Okay? Another nice thing that you'll find is that when you do the Hubbard-Stratonovich in the language of magnetism, because in the exchange channel, like if you write S.S or M.M, whatever you call your magnetization interaction, it's actually attractive. When the interaction is repulsive, the magnetization is attractive in the sense that it's ferromagnetic. Because ferromagnetic maximizes the exchange interaction. So then the Hubbard-Stratonovich is without an I. That's why you get here a minus instead of plus. Okay? Very, very deep. Very deep. Okay. But another point I wanted to make, I don't even remember what I wanted to write. I wanted to tell you when this works. So 1, large N. So we can multiply the number of fermions, and then you'll find that these diagrams, because there's an internal sum over n, are enhanced by a factor of n compared to all other diagrams. 2, weak coupling, let's say, weak. So that's when E squared over 4 pi epsilon Vf is much, much smaller than 1. This is, if you like, just the fine structure constant. For a Fermi surface, they call it Rs, because Vf is not just a constant speed. But it's basically just a defined structure for the specific Fermi velocity. And then the last thing is Migdal. So Migdal says that sometimes you'll find that the vertex correction is much, much smaller than the original vertex. That typically happens when when the boson is slow. Slow bosons, like phonons. So these are all reasons why the theory becomes semi-classical and sign problems disappear. Now the last thing I want to do is I want to talk about the plasma frequency, because specifically for the Coulomb interaction, if we're already here, let's talk about the resulting interaction for a moment. So I just want to point out that VQ1 plus pi of Q, V of Q, if we remember that VQ is 4 pi E squared over epsilon Q squared, and we remember that 4 pi E squared n of 0 is Q Thomas Fermi squared, okay? Then what we get is that when VFQ is much, much larger than omega, Q is much, much larger than omega, then this thing becomes 4 pi E squared divided by Q squared divided by Q squared plus Q Thomas Fermi squared. Okay, and this is the limit of Thomas Fermi screening. If you Fourier transform this, you're going to get a Coulomb interaction, 1 over r, but with an envelope that decays exponentially, and the typical length scale is 1 over this Q Thomas Fermi.
That is the Yukawa potential.
It is equivalent to a Yukawa potential, yeah. But this is static. Okay. And the second limit is VFQ much smaller than omega. In this case, we have 4 pi E squared, and then we have you know what? Then we have Q squared, right? And then we have plus 4 pi E squared density of states. Oh, sorry, this is with the VF. I think this is VFQ squared. Ah, yes. Yes, it has to be from units because you need energy over energy density of states. So then you have energy, and then you have here VFQ squared over omega squared. Actually, there's a 3, if I remember correctly. Okay? Now, what did we get here? This guy is, I can rewrite this interaction. I can rewrite this interaction as 4 pi E squared over Q squared. And then I have omega squared divided by omega squared plus omega plasma squared. where omega plasma squared for me is 4 pi e squared n of 0 VF divided by 3. Oh, and here I'll write epsilon and epsilon. Now I can rewrite this thing, right, as 1 minus omega plasma squared over plasma squared plus omega squared. And another thing I want to comment is that if I analytically continue this to real frequency, then this becomes a minus. Okay? So this is a 0. Okay. So wait a second. So if I take omega to 0, this becomes 0. Yes. Probably this is correct. Unless I didn't miss anything. So something is bothering me. So if omega is very, very large, omega becomes small. Oh yeah. So what you're basically seeing from this is that this field phi has a pole, which is the plasma frequency. And in the static limit, we get Thomas Fermi screening. So I think this is one of the examples. And in the exercise, I'll try to give you another one where you can see the power of field theory in general. Because, you know, if I would want to derive all these results, you know, from like, say I just taught you, I don't know, like the Schrodinger equation. I showed you how to write like fermions in a, or I can do it. I don't have to. Well, this is quantum. Okay, let's start from the fact that this is quantum because there's a density of state. So I don't know. I taught you Sommerfeld theory for free fermions, like I did in the. I'll actually teach you in condensed matter in a moment. I'll teach you plasma frequency. But you know, if I want to do plasma, I need to come up with some. Thomas Fermi is actually even more difficult. I need to do some like self-consistent calculation. They teach it sometimes when they teach you atomic, like the hydrogen solution, and they look at like heavy atoms. They start doing. You need to kind of self-consistently stick it in the Poisson equation and get all these things, and you know, like, and in field theory it's just like all these results, they come out naturally, and we didn't do anything. All we really did was complete a square, you know, expand stuff, no physics, like we don't know anything about the physics, no self-consistency, nothing, and all this beautiful physics, which is very hard to interpret, like you need to think about it, of, you know, like, you know, all these stories about plasma. Did you ever hear about this? You know, one way to think about like the plasma frequency is to take like a material and then imagine that the electron cloud is being displaced like this, and then you kind of develop like negative charge here, minus sigma, and here you have plus sigma, and then it's like a capacitor. And it's oscillating, and you can get a frequency from that because there's a force that wants to restore the electrons, and then they oscillate like that, and that's like your plasma frequency. So all this, you know, all this physics, or this guy is telling you that, you know, if there's an electron here, right, and it's surrounded by other electrons, then they kind of get repelled outwards, and then you get like effective positive charge surrounding it, and it's screened, and, you know, all these beautiful pictures, and it's all encapsulated in this quantum field theory. We didn't need to do it, and I can even tell you that recently I had this annoying experience where some people. So I wrote a paper when I was in my postdoc about superconductivity from plasmons. So you can interpret these plasmons like phonons, basically, because they contribute some attractive. You can interpret this part like a repulsive part to the interaction, and then an attractive contribution from the plasma. So I wrote a paper about that in some material where they see superconductivity at very low density. It's called strontium titanide O3. And this material, it's a superconductor, despite the fact that you can dope it with like 1 particle per million atoms. So very, very low density. And then what you have is like omega debye is 100 millieV, and EF is like 1 millieV. So EF is 100 times smaller than the Fermi energy. Sorry, omega debye is 100 times larger than the Fermi energy. And then this Migdal thing is completely out of the question. All the standard theory for superconductivity breaks down. And then people try to explain. Okay? So we use this plasmon frequency because it turns out that in this material the plasmon is very small. It's even smaller than the Fermi energy. So we were trying to make up some story. It didn't actually work that well. So our conclusion was kind of, we said it doesn't work that well. Now people are talking about some ferroelectric quantum critical point, and our postdoc Sudeep is writing papers on that, for example. But then these annoying people from I don't know, from the States, they wrote a paper claiming that if you have multiple polar phonons in a system, because this is a complicated atom. So by the way, when I say polar phonons, I mean optical phonons. Optical phonons are polar if the 2 atoms have different charges. And in ionic crystals, that's the situation. And here you have, this is a complicated crystal, so you can have many different optical branches. I said if you have many optical branches, then you can have over-screening. Basically, you know, this optical phonon reacts and that one, and overall they overreact and they create an effective attraction between 2 electrons. Because they overscreen it, they make a positive charge. So it looks to another electron like a positive charge. That's basically what they're saying. And the point is that this mistake was already made before by the great Gorkov. When I was writing this paper, we noticed that Gorkov, he had a very, nice argument and all, but when we stripped it down to the bone, we understood that in the core, that's actually what he's claiming. There's overscreening. Then we wrote, to him that he's wrong, and we had this debate, and eventually he admitted it. Okay? So then I write to these guys, I tell them, look, this is the mistake exactly Gorkov did, same thing, and they were arguing with me like mad. And then eventually I said, okay, I'll just show to you that you're wrong. And the way I did it, I'll give you, it's such a simple calculation that you guys can do it with what you know now. And it's amazing to see how you can get all sorts of very complicated relations, which if you open Ashcroft and Merman, there's like 15 pages of like, imagine a harmonic oscillator, which is actually a charge on a spring, and now let's multiply them, and let's do this, and let's do that, and all this. And in quantum field theory, just complete a square twice, and boom, you get the result. Really, it's that simple. So I'll let you see that, and this is just an example of the power.
They admitted you?
No, they never admitted. I wrote a comment. No, I can tell you that. So first of all, I am a very problematic scientist because I argue with people a lot. So it happened to me many times, and I had this argument with Gorkov, and then later we had an argument with some other guy from Germany, and he admitted it eventually, but they all come out, they admit it, but then they also come out with a sting, like they say, yeah, but what you did is complete bullshit because of something, or whatever. So they admitted their mistake, but these guys know. They just, so the way it went is initially I told them I think, I gave them general arguments why what they did is wrong. But they said, no, but if what you're saying is correct, then all these fabulous and important theories are wrong. I said, no, I'm not saying that, because I'm talking specifically about your theory. I don't see why this and that paper are wrong. Also, only what you did is wrong. And then they didn't believe me. So eventually I said, okay, I'll write a note. I'll do the calculation, because I knew that it's just completing a square twice. So I said, okay, I'll take an afternoon. I can complete a square twice, instead of reading, I don't know, Oz's last note on thermal conductivity, which I'm late on. So I completed the square twice, and I sent them this thing. And then they said, now that we've seen your thing, we're okay. They said something like, basically what I did is I rederived their result, but just I showed them exactly where I'm making the mistake. Like, I made the mistake deliberately, and then I got the result. And I said, now let's not do the mistake, and I got a different result. So they said, now that we've seen this, we're even more certain, we're more confident. And I was like, I wrote to them, I understand that you're confident, but I don't know why. That the fact that you're confident, I got that. But the question is, where this confidence is coming from, I don't know. So I was very aggressive, which is probably the main problem, but they never admitted it. So I wrote a comment, and I don't know what's going on with their paper. I didn't see it published.
Does going back on your statement as a scientist really discredit you so much in the eyes of the community?
What?
When you go back on a statement or a paper that you publish, does it discredit you so badly that they refuse to do it?
Look, it depends. It depends. If you're like consistently making mistakes all the time, like, if people know that reading your papers are often filled with mistakes or wrong statements, then okay, making mistakes in science is a big, it's a long discussion. First of all, there are different kinds of mistakes. There are mistakes that are interesting, and mistakes that are stupid. And then there's also how you react to mistakes. So everyone makes mistakes. If someone comes to you and tells you, look, this is a mistake because that and that, and you reason, people won't discredit you. Now, if you make a lot of mistakes, like, there are scientists, I won't say their names, which everyone knows that they make bold claims. Majorana this, and spin liquids, and I have emergent particles, and they're doing this and doing that. And people already went through this process again and again and again, checking, and eventually found that they were too hasty on their statements and stuff. That can sometimes discredit them. But what I find, empirically what you find, is that these guys become very famous. They get invited to all the conferences, but just behind their backs, everyone says, yeah, we know that's it. So that's one type. And but if someone is just making stupid mistakes and being stubborn about them, that will discredit them. But every once in a while, everyone makes mistakes. And the most important thing is that mistakes are important, because we learn from mistakes. So you shouldn't be afraid of making a mistake. You have to, if you think that something is right and you checked it in all possible ways, then yeah, go ahead. Don't be afraid of making a mistake. No, it won't discredit you, especially if it's something that only happens once in a while and not constant. Yeah.
Return to this.
Yes.
So these expressions are for the average of the field, like.
For the average of the field. Yeah. This is within RPA. This is an RPA result.
What does it represent in reality? Because it's like auxiliary field. How did you connect it to the plasmas there?
So that's okay. First of all, that's a connection that we're making. I'm showing you that this auxiliary field is not completely detached from any intuition or any reality. We saw that when we did the Hubbard-Sultanovich transformation, it coupled to density. Okay? So I showed you that we can, in the bare level, before we took into account the effect of the electrons, the correlator of phi gave us the bare interaction. So now I'm allowing myself to continue to interpret the correlator of phi as the interaction between electrons. But now I'm taking into account the self-consistency of the electrons. Now, I agree with you that it's much, much less concrete than what we did when we did perturbation theory. Because when we did perturbation theory, what we said is, we said, I want to compute a correlation function. This is something, this is basically an amplitude for scattering or something. I'm just computing it, and by hand I'm working the machinery, and I'm getting this or that result. But I'm showing you that this gives the same result. It gives the same result, and it tells you something that quite generic, that this correlator is at least to everything we understand. It gives you the RPA interaction self-consistently, and it's much easier to compute than well, it's not much easier. I don't know much easier, but sometimes it's easy.
And how did you connect it to the plasmons? Like, what did you do?
How did I connect it to the plasmons?
Oh, like you wrote an expression with the plasmon frequency, but what does it equal to?
What do you mean by that? This is the plasma frequency.
Oh, okay, but what's the expression there?
Which expression?
Above the Q. In the middle. No, left. Yeah. Yes.
This is the. Oh, sorry. This is this.
It's the correlation.
It's the limit where VFQ is much smaller than omega.
Okay.
This is the Coulomb interaction at the RPA level.
Okay. And what does it represent physically? Like, what's this region represent physically? VFQ smaller than frequency.
It's the dynamical regime where. So this is exactly what I was drawing here. We're talking about very long wavelength frequency. Okay, so this is the limit. The way you should think about it is the limit where Q is going to 0. So very, very long wavelength limit, and that's why I'm displacing the entire electronic cloud as 1. That's like basically Q equal to 0. And what you see is that even when Q is going to 0, we have a frequency. Okay. And the way we can understand this is this capacitor business. This is not like you can. The point is, the way you should think about it is that the Q here, Q, is like 2 pi over L, right? Because it's the entire system in a box. But now, as I take L to infinity, you see that this thing still has the same frequency, which is independent of L, as I take it to infinity. So that tells me that the frequency remains finite even in the thermodynamic net.
Interesting.
Okay? Yeah. And if you want to think about it at finite Q, you can imagine basically these modes are this is density modes. It's longitudinal modes. It's basically, imagine that you have many electrons. Okay? And then you have like regions where they're more dense, and regions where they're more dilute, and regions where they're more dense, and regions where they're more dilute. Like, I don't know if I'll try to. You see what I mean, okay? Yeah. And then here in this region you'll have like plus, and here you have minus. Okay, so it's like a wave. And then these waves are like capacitors. It's like capacitors, and then they create this long range. And this is unique. This effect is unique to a long range interaction. It's crucial that we have a long range interaction. And by the way, this whole story is actually in a different way related to the Anderson-Higgs mechanism. So because you have to remember that phi, the potential, is actually a static limit of a photon. Right? A photon is a gauge field. It's basically related to a gauge field. Gauge field, you know, you have gauge invariance and so on, that makes sure that this is the word identity that makes sure that the photon remains massless, right? But there is a mechanism in which the photon can develop a mass. So you know that the story is that, you know, we have a mass. The same, so that the beginning of that is that the Z and the W develop a mass, which are gauge fields, the gauge bosons. And the way they develop a mass is because the Higgs boson condensed. So in order to develop a mass, you need something to condense. What condensed here is charge. So the charge is related to the photon. It couples to the photon, which is its gauge boson, and it condensed, and that's why the photon developed a mass, and that's why this is shiny, because the photon can't come in. Okay, it's expelled. It has a finite mass.
Like the Mike effect.
So here's the point. The point, and this is an important point, that here the boson, the charge condensed, but it's not coherent. And because it's not coherent, some parts of the gauge field can leak in. And that's the magnetic field. So in order for it to also expel the magnetic field, it needs to become coherent, a real condensate. And to really condense, it has to become a superconductor. And only when it becomes a superconductor, you get the full effect, which is what we call Meissner. But actually, this is a very subtle issue. It's very delicate. The beginning of the effect is already present. Like the metal, it already does almost all the job. Like almost, you know, nothing is coming in. No photon is coming in at any finite frequency. The only thing that can leak in is a static magnetic field. That's the only thing that's left to repel. And that's the effect of a very subtle situation where you have charges that basically represent the fact that electric charge is condensed, but it's not coherent. And in order for it to become coherent, because this, by the way, the fermion itself can be viewed as a charge boson times, you know, a fermion, which is not charged. So that boson is basically condensed in the metallic state, and we can understand this via this method of fractionalization. Maybe I'll give an exercise on that. But the point is that they're confined to each other, and in order to, you know, make it, in order for this boson to become coherent, you need to create these Cooper pairs, and these Cooper pairs condense, and only then you get the Meissner in full. So that's another story about what happens when you have this kind of partial condensation. So that's a different question. I never thought about this, but it could be that the Higgs is not really that coherent. I don't know how crucial. Yeah, I don't know, but probably it is. Like according to standard theory, we live in a coherent condensate of the Higgs field, and that's what gives us a mass. Okay, so now what we want to do is we want to do linear response theory. So let's at least start linear response theory. Linear response theory is going to connect very nicely to many things we did, because, you know, we can use perturbation theory and field theory and path integrals to compute response functions. That's one thing that is going to connect for us very nicely. And also, well, I don't know what else. We'll see. I don't remember. Yes, I know. A very important issue. because we know how to compute correlation functions in Matsubara space. So we get a lot of Matsubara correlators. But the question is, how do we connect that to, you know, real space-time correlators that you would measure in the experiment? This we're going to get from linear response. Okay? A very important intuition. So we start from considering a Hamiltonian which is divided into some static term, okay, and what we will call an interaction. And what we call an interaction. It doesn't have to be really an interaction, okay, and this part H0 can be interacting, okay, but we call this interaction in the sense because it's the interaction with the field. So here there is some probe field, something we're shooting in the material, and this is time independent.
So you only need something that breaks time reverse time, and something that.
Well, it's some time dependent, yeah. Time dependent field. It's more than just breaking time reversal. Okay, it's more. It's breaking time translations. Okay. Because time reversal alone, you could have magnetism or something. So if you like, you know, H0, if you want to imagine, let's imagine that H0 is just, you know, some, even a one-dimensional, you know, phonon, like a harmonic quadratic phonon thing or whatever, like elastic medium, quantum elastic medium. And this V of t is something so there is some field F, a driving force, and phi couples to this phi. Continue here, this. And then the general notion, as you know from classical mechanics, you know, in the course I teach for differential equations, for example, you know that what you expect is that generally you can compute something like delta phi of x and t, which is something like psi of t Let me write it like this. So I have here something like phi of x and t, expectation value, minus phi of x and t, 0. What is this 0? I just want to say that if this phi has a finite expectation value under h0, then I'm subtracting. Okay? But for the theory we wrote, this is 0. So you can just think about this delta phi as the expectation value of phi. The point is I want to write this thing as a response. I want to write it. So this is like a mixture between quantum. So this field is a quantum field. This is a quantum average. This is a classical. You know, this is like a number, expectation value. I want this expectation value of the field to be some response to the classical field. Notice that this is also a classical field. This is an operator. This is a field. Okay, maybe let's denote the operators with the hats. So we remember what is an operator. Okay. and then we have something like dx, integral from minus infinity to infinity dt, chi of t minus t prime, and x minus x prime. Assuming that there is translational symmetry both in t and x, times this field x prime and t. So this chi is what we call the linear response function. And this is our guide. This is what we're after. This is what we want to compute. And this is our goal. Because if we know this, we know how the expectation value of the field responds to the field. Okay, in the linear level. Okay? And there are many, many probes that measure such a thing. Okay? Because if we're shooting light at the material, then this is a coupling between, say, the gauge field A and the current of the electrons, for example. Okay? And if we're driving, if we're driving a current, okay, then this thing will be E, like an electric field or a voltage, and this will be, again, like electronic current. What else? So if you're shooting X-rays in the material, then X-rays couple to density. So this field will be, your X-rays, and this will be the density.
Also with magnetic fields.
Raman, yeah, magnetic field. Yeah. If you're applying a magnetic field which is time dependent, then this would be magnetization in the sample, and this would be your magnetic field that you're applying. So it's a recurring thing, and people measure this chi in many different ways. And we want to know how to compute it theoretically, so we can make predictions for different phases of matter and so on. So this is the goal of this. Okay, so now I want to remind you that there are basically two pictures.
Can I ask a question?
Yes.
I'm taking here a thermal camera. No.
So that I don't want to specify right now. So eventually what we will learn, in this course what we'll learn how to do is to compute a quantum thermal average of the sort that we learned how to do, right? The whole point of this path integral is to compute a quantum thermal average.
Yes.
And now we're going to compute, like, imagine that I perturb the system, and then I measure its response to that perturbation within, around or close to thermal equilibrium. Yes.
Okay.
But
yeah,
right,
it's not really an equilibrium. You can
It's
use
not.
partition function, but you're using them anyway.
No. It's deeper than that. We'll see. Right? It's not some hand wavy excuse. It's going to be rigorous. Okay. But what I wanted to remind you is that we have, the Schrodinger picture is to say that an operator, an average like this over an operator is basically psi of t O psi of t, right? And psi of t is basically e to the minus h over h bar t, or let's take h bar to 1 because I'm tired. H bar t psi of 0, okay? And then the Heisenberg picture is where O of t is basically some psi which is constant in time, but we're evolving O of t and they're both equivalent, right? Where psi of t, where O of t, the evolving operator, is e to the I h t, O of 0, e to the minus I h t. And they're trivially the same thing. But actually, we're not going to want to use this or that. Okay? We're going to use a third picture, which is known as the interaction picture. Did you ever encounter the interaction picture? No? So in the interaction picture, we basically, it's kind of a hybrid between the two. So we're going to evolve both wave functions and operators.
Oh, I think yeah.
You know this. Okay, so we denote it like this. So OI of t is going to be e to the minus h naught t, O I h naught t. So the operators evolve with the free part of the Hamiltonian, the part that is time independent, and the wave functions are going to be compensated. It's going to be e to the maybe like this, probably like this. I think it's like this, and then this is going to be h t e to the minus I h t. Okay, one moment. So here, first of all, this is kind of vague because h depends on time. So you know that when h depends on time, there's a more generic evolution operator, which is actually a time-ordered integral, which we will develop in a moment. But you could imagine that that's what's written here. So, but I don't want to use u because I'm going to use u for something else. So you could imagine that this is like, evolution operator. Now the point is that this is trivially the same, right? Because you see that if I take an expectation value psi I of t, OI of t, psi I of t, I get the same expectation value.
It's depend if the commute is the free part of the Hamiltonian or not. Because
no, it doesn't. It doesn't, because this cancels that, and then you get the original evolution.
But for Hausdorff-Baker, you need to watch the commutator, right?
Which commutator?
Like it's not.
Okay, let's write it explicitly, and then you guys can complain. Okay, so I write this explicitly. I write psi I of t, OI of t, psi I of t is equal to psi of 0, and then I have e to the minus I h, the full one, and I do an integral blah 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 blah, e to the this is with a plus e to the minus I h naught t. Okay, that's evolving this thing.
Mm-hmm.
Then I have this guy, so I have e to the I h naught t, O of 0, e to the minus I h naught t, and then I have the other guy. I have e to the I h naught t, e to the I h e to the minus IH. T and psi of 0. And all I'm claiming is that this is identity and that this is identity. And I don't need Haus, Beekdorf, whatever, Schmechdorf, Beisdorf, and I don't need anything to commute with anything. Okay? This is just by definition.
Which is okay. But you're claiming that we are evolving the wave function only with the interaction. This is
No, I didn't.
commute.
No, I didn't say that.
Ah,
I
okay.
said we're evolving it with this.
Okay.
Okay, this is a very different picture, but it will be just the and you'll see that, and you'll be surprised. You'll be surprised by that. But for that, you'll have to wait till next week. Okay, so that's something to keep you במתח. Okay, and I'll try to write a exercise, but I don't have time. I'll try. So we'll try to have something like 5 exercises for this course. I hope that's enough.
Regarding the test.
The exam. Yeah, I need to move it.
Yes.
But I need to remember to send you an email. I'll try to do it right now when I go to the office. I'll send you guys an email.
What is the expected age?
I don't know. What do you guys prefer?
Maybe. טוב, אפשר באמת. נראה לי לפני המבחן המקורי, כי פשוט, יש איזה, המבחן הוא במקור שבועיים אחרי סוף הסמסטר, אז יש כאילו שבועיים, לכאורה די ריקים. הסמסטר נגמר בתחילת יולי, המבחן אמור להיות ב-15.
לא, זה יהרוג אותי לעשות את זה. לא. תן לי איפשהו באוגוסט משהו.
אוגוסט גם כבר, פשוט נראה לי כבר נכנס למועדי ב' בהגדרה. יכול לבדוק את זה רגע. באפליקציה.
למה? אתה עדיף לך כשלפני שתחילת החופש הגדול.
לא, הבעיה העיקרית זה שאני באמת במצב של, אני מכין את השיעורים ערב לפני וכזה, ואז אני ממש אסיים את הסמסטר עם הלשון בחוץ, ואז אני נוסע לאיזה כנס בוונציה, שבוע אחרי זה אני נותן הרצאה ב-IPS, ושזה בדיוק זה. אז מה שאתה אומר לי זה אתה רוצה להזיז לי את זה קודם מאיפשהו לתוך הכנס.
כאילו המועד ב' של הקורס זה ב-17 באוגוסט.
אז אולי נעשה את המבחן המקורי במועד ב', ואת המועד ב' לא נעשה כי כולם יקבלו 100. מה דעתכם?
אני בעד. לא מתנגדים.
מה השלב הבא כאילו האינטראקשן? הם עוברים לאיזשהו טרסט פיקצ'ר
מה בזה? כן, מה, נו.
כאילו אמרת אתה שומר את ה-U, אני יודע למה ה-U משמר. כאילו לפחות אצל המנואל.
מה?
זה הטרנספורמציה שאנחנו עושים כאילו למיתוניית כדי לעבור לאיזושהי טרסט פיקצ'ר, ואז אין טוב שאני לא תבוא זמן.
אתה יכול לחשוב על זה בתמונה של dressed picture? אבל אם אתה חושב על ה-rotating phase approximation או משהו כזה, זה לא הכיוון.
זה לא הכיוון?
לא. זה הרבה יותר בסיסי, פונדמנטלי ואלגנטי. מה שאנחנו יכולים לעשות זה, אין פה שום approximations.
כן,
מדויק.
זה קורס, כאילו בעצם